The last lecture we started support vector machine. For the moment, we are considering the hard margin support vector machine, means the case that two classes are linearly separable. Then we will see that when the classes are non-linearly separable, how we can extend support vector machine to that case. So for the moment, our data has this form. So I have n data points, and yi, which is my class label, is either 1 or negative 1. Okay? And data is linearly separable. So when data is linearly separable, there are infinite number of solutions to make distinction between two classes. So we are talking about binary class. So I have two classes of data, and there are infinitely many linear decision boundary which can make distinction. We learned in perceptron, perceptron is going to find one of those. But in support vector machine, we are interested in a unique solution. We are interested among all of these possible solutions. We are interested in the solution which has maximum margin. Means the distance of this decision boundary to both classes are maximum. Okay? So we then we went through the geometry of this decision boundary, which in general we show it by beta transpose x plus beta null. And we learned that beta is orthogonal to this decision boundary. We also learned that if you would like to find a distance of any point to this decision boundary, we can simply put that point in this formula, beta transpose x plus beta null for any x would be the distance of that x from this decision boundary. So if it's 0 means it's on the decision boundary. If it's non-zero means it's not on the decision boundary. So anyway, di, we learned that would be beta transpose xi plus beta null for any xi. But di could be also, we learned that di could be positive or negative, depends on the side. If you're on this side of the decision boundary, this di is negative. If you are at the other side, di is positive. So if you are interested in distance, the real concept of distance, which is always positive, the distance would be yi times di. So that would be the distance of xi from the decision boundary or from the hyperplane. Okay, so what would be the margin? The margin is the distance of the closest point, right? So for any point, that would be the distance, yi times di. So among all of them, I'm interested in this distance, which is the distance of the closest point to the decision boundary, which I call it margin. So margin would be the minimum of di yi for all xi's. So we covered up to this point in the previous lecture that this is the margin, and we would like to maximize this margin. Okay, this margin is basically minimum of yi times di when di is beta transpose xi plus beta null. And don't forget that this needs to be normalized, I mean, that was true if beta is normalized. If it's not normalized, you always need to normalize. Okay. So that's going to be my margin. Okay, now yi times beta transpose xi plus beta null is either 0 or greater than 0. It's distance, right? It's always non-negative. For points that are not on the decision boundary, it's always greater than 0. So for any point that's not on the decision boundary, it's always greater than 0, right? So that's for all xi that are not on the hyperplane. Okay, if for points that are not on the hyperplane, it's always greater than 0, means there is always a distance between this point and the hyperplane. So there's always, a constant c. There's always, some constant such that, there is always a c such that this yi beta transpose xi plus beta null is greater than equals c. Right? So I have this decision boundary. Suppose that, any point which is not on the decision boundary, yi times beta transpose xi plus beta null is greater than 0. Means there is a distance here. So the smallest distance, call it c. So the smallest distance, call it c. So there is always a c such that yi beta transpose xi plus beta null is greater than equals c. Okay? So I can divide both sides by c. So I can say that yi beta transpose c xi plus beta null divided by c is greater than equal 1. Right? So call this beta transpose divided by c, or beta null divided by c, beta star transpose, or beta null star. Okay? So say this is in U so if I write it this way, then I can say that yi beta star transpose xi plus beta null star is greater than equal 1. Okay. So it means there is some weights, if I rescale beta, and if I rescale beta null, always, I can satisfy this condition. For some beta, I would like to define this hyperplane. Beta, basically, it doesn't matter, right? It's just a vector. In principle, it's a vector which is orthogonal to this decision boundary. So it tells me basically the direction of this decision boundary. The length of this beta doesn't matter. It's longer or shorter, it doesn't matter. I can rescale, it doesn't change the hyperplane, So I can always rescale it in a way that this condition is satisfied. So for some beta, from now on, I even don't call it beta star. For some beta, this is true. Okay? So for some beta, the lower bound of distance is 1. You have a hyperplane and you have some points and they have some distance. You can always rescale your space in a way that the shortest distance is 1. This is basically by rescaling beta, you're rescaling your space, such that the shortest distance is 1. So if the lower bound is 1 for some beta, means that this quantity for some beta is 1. And if I'm interested in minimizing this, the lower bound of this quantity is 1. So I have to minimize this and I have to maximize this. But beta, we fix beta, we rescale beta, and now beta is, for some beta that has been fixed for some norm, this is 1 at least, the minimum is 1. So it means that my margin, which was minimum of this fraction, I can literally put 1 here. So I can say that my margin is 1 over beta, the norm of beta, for some beta. Now, knowing this, I can form an optimization which solves my problem. From the beginning, I wanted to maximize this margin, and now I computed margin in terms of the norm of the vector, which is orthogonal to the hyperplane. I was looking for that hyperplane, which maximized the margin. Okay, so to maximize this margin, I have to minimize the norm of beta. So basically, I can form my optimization problem now this way. I'm looking for a hyperplane such that the norm of beta of that hyperplane, the norm of the vector, which is orthogonal to that hyperplane, is minimum. And beta transpose xi plus beta null times yi is greater than equal 1 for all xi. So I have to make sure that this condition is satisfied, because we rescale beta such that, the distance of the closest point to the hyperplane is 1. I have to make sure that this condition is satisfied. And among all hyperplane that can satisfy this condition, I'm looking for the one which has minimum beta, minimum norm beta. That's my optimization problem. So I have to make it more concrete. What do I mean by norm of betas? Let's do, I put 1/2 here and beta squared. If I don't put 1/2 here, nothing will change except that when I take derivative, it would be easier. They cancel each other. And instead of norm 2, I can do norm 1 in principle, but I cannot take derivative. So I go for norm 2. So norm 1 would be, norm 1 support vector machine by itself would be very interesting problem. But this is norm 2, okay? So this is my optimization problem. I have to minimize this subject to this constraint. Okay, so what should I do now? I have a constraint optimization problem. Right, Lagrangian, right? So I can form Lagrangian of this objective function. And Lagrangian is a function of primal variable, which is beta and beta null, and dual variable. So how many constraints do I have here? Sorry? Number of points, right. So I have n constraint here. For each point, I have one constraint. So I need n Lagrange multiplier for each constraint. So basically my Lagrangian would be 1/2 beta square minus sum of alpha I yi beta transpose xi plus beta null minus 1. Okay, that's my Lagrange. I had n of them, n of these constraints, so I sum over all. And alpha is Lagrange multiplier. It should be greater than equal 0 for all I. Okay. We can solve this problem. It's a quadratic problem. We can solve it. But if we look at the dual of this problem, the dual would be easier to solve and has very nice properties that we can see. So instead of solving this primal problem, we are going to look at the dual of this and solve the dual. Okay. My Lagrangian has 3 parameters: beta, beta null, and alpha I. So I need to take derivative of this Lagrangian with respect to primal variable beta and set it to 0. I need to take derivative with respect to another primal variable that I have beta null, set it to 0. And if I take derivative with respect to dual variable alpha, always it gives me, it gives the constraint back, right? So take derivative of L with respect to beta. So the first term is 1/2 norm of beta squared. So what would be derivative of this first term with respect to beta? Sorry? It's going to be beta. So the second term, I have, I have alpha I yi beta transpose xi, and I have alpha I yi beta null. So alpha I yi beta transpose xi with respect to beta would be alpha I yi xi, right? And it has a summation, of course. And I have another term, alpha I yi beta null with respect to beta is 0, right? So here only I have one term, alpha I yi xi, when I take derivative with respect to beta. So it is minus sigma over all I, alpha I yi xi. And this needs to be 0. It means that beta should be alpha I yi xi over all I. It basically tells me how my primal variable, basically the relation between primal variable and my dual variable, alpha and beta. Now let's take derivative of L with respect to beta null. If I take derivative of L with respect to beta null, what would be the first term? 0. Then I have alpha I yi beta transpose xi with respect to beta null, 0, right? I have another term, alpha I yi beta null with respect to beta null, would be alpha I yi, right? So that's going to be just alpha I yi equal to 0. So I have to make sure that this is also true. Now if I take derivative of lambda with respect to alpha, you can see that you get your constraint back. It's always the case, right? If you take derivative with respect to dual variable, you get your constraint back. Okay, so I mean, this tell me what's the relation between my primal variable and my dual variable. So if I want to write the dual optimization problem, I can substitute this beta in what I have here in the original formula and see what's going to happen. Okay, so it's going to be 1/2. I have norm of beta squared, which is basically is beta transpose beta. You know, this term is beta transpose beta. So, and I know this is beta. So I need beta transpose, which is alpha I, alpha j, yj, xj transpose, or I transpose makes no difference, okay? It's just index. Times beta, alpha I, yi, xi. Okay? It's the first term. And, you know, these are the indices of this tree are j, so I can push them inside. And I can write this as summation over j I x j y j x j transpose xi, or vice versa. You know, I can write it as alpha I, alpha j, yi, yj, xi transpose xj over all I and j. And I have 1/2 here. That's my first term, beta square. Okay. So what about the second term? You know, I'm going to expand this term here. You know, I had this alpha I greater than equal to 0. So let me expand this term. It is summation of alpha I, yi, beta transpose xi. And then I have alpha I, yi, beta null, right? And I have minus alpha I. That's summation of this part. I mean, expansion of this part. And this beta transpose can go outside this summation. So it's like beta transpose alpha I, yi, xi. And this beta null can go outside. So it's beta null alpha I, yi, right? And then I have this alpha I. Okay, now, if I want to write it in terms of the dual variable, I have to write this beta transpose in terms of my dual variable, which is summation of ai, alpha I, yi, xi, transpose, right? So basically, it's going to be negative. You know, beta transpose would be alpha I, yi, xi transpose, and then I have another summation, alpha I, yi, xi transpose. So it's exactly has this form, right? So it's summation of I, j, alpha I, alpha j, yi, yj, xi transpose xj for the first term here. Then I have beta null alpha I, but summation of alpha I is 0. So the second term will be 0, right? And then I have this term, negative of summation of AI, and there's a negative sign also here, so plus AI. And alpha I is greater than equal 0. And AIYI is 0. You know, we have to make sure about it. So these two terms I can simplify. So I can write everything as summation of AI, alpha I basically. And I have 1/2 of this term minus the term, so it's going to be negative 1/2. Alpha I, alpha j, yi, yj. Xi transpose xj. Subject to the constraint that alpha I is greater than 0 and sigma alpha I yi is 0. You know, my unknown is alpha now. You know, I wrote everything in terms of my dual variable. I don't have my primal variable anymore. This is an optimization problem. Should I minimize this or maximize this? You know, originally we wanted to minimize this. We wrote the Lagrangian in this form. And now everything is in terms of the dual variable. Do you maximize or minimize? Sorry? Minimize? Who believes minimize? Who believes maximize? Okay, why maximize? Exactly. It's like saddle point problem. You know, when you write the Lagrangian here, basically the optimization would be maximize of alpha, minimize of beta, or whatever, beta null. You know, what would be the maximum alpha which minimize this, you know? Now everything is in terms of alpha. So basically, I have to maximize it. You know, I don't have. You know, it's like you want to minimize this function, and you find the dual of that, and you have to maximize that one. Okay, so we need to maximize this and find alpha. So, so how can we do this? You know, I have this problem. You know, I have to maximize this objective function, and I have some constraint. First of all, you know, constraint in terms of alpha are linear. You know, alpha I greater than 0, and this alpha I yi equal to 0. In terms of alpha, these constraints are linear. In terms of alpha, this function is it linear, or it is? It's quadratic, right? In terms of alpha, it's quadratic. So a quadratic objective function subject to some linear constraint. What type of mathematical programming is that? Linear objective function subject to linear constraint is linear program. quadratic objective function subject to linear constraint is quadratic programming, right? So it's quadratic programming. So we can solve this efficiently, and it's a convex problem. Because quadratic objective function is convex. Let me write it in matrix form. I can write everything in matrix form. So let me define matrix S such that Sij is yi times xi transpose, or let me write it here, times yj xj. I multiply this yi to this xi. Yi is a scalar. It's either 1 or -1. But x is a vector. I multiply this yi to xi. I multiply this yj to xj. Then assume that you have a matrix such that each element of this matrix is element ij is yi xi transpose yj xj transpose. So it's n by n matrix. So if I have this n by n matrix, then and I define alpha to be a vector of alpha 1 to alpha n, and I define y to be a vector of y1 to yn. So if I have this, then I can write summation of alpha I. So I can write it as like alpha transpose 1. When 1 is, let me write it E. E is a vector of all 1. 1, 1, 1, 1, 1. So E transpose X would be summation of alpha, right? Alpha is just a vector transpose times a vector of 1. So you basically sum all of the elements. So minus 1/2. Then when I have this matrix, I can write this as alpha transpose S alpha. It's just a quadratic form. And then this vector is greater than 0. And this summation alpha I yi is simply alpha transpose y. This is 0. So in matrix form, I can write it this way. And I have to maximize this for alpha. This is quadratic, clearly, in terms of alpha. If S is positive semi-definite, this is convex. If S is not positive semi-definite, it's not convex. Even if S has one negative eigenvalue, it's not convex problem. Is it, can we say that S for sure is positive semi-definite in this case? By construction, it's positive semi-definite, right? By construction, it's positive semi-definite. This is the way that I made S as, multiplication of these two matrices. So it is positive semi-definite. Any question? Is it clear? It's not clear, let me know. Explain more. Okay, so it is a convex problem. So I have a convex quadratic objective function subject to linear constraint. It's quadratic programming. It's a convex problem. It has, I can find global minimum of this problem. That's the beauty basically here. That, in perceptron, we had infinite number of solutions. The objective function was not convex, and we could trap in a local mean. In neural network, the objective function was not convex. We could trap in local mean. We had gradient descent. So here, the objective function is convex, and I can go right at the global minimum and find a unique solution for this problem. in optimization, most likely, most of you, I think, are familiar with KKT condition when you're doing, primal, dual, Lagrange multiplier. Even if you're not familiar, we don't want to basically use this in detail. Just the only thing that we would like to know is that if you want to minimize a function like fx subject to the constraint that gix is greater than equal 0 for all I, then the necessary condition for the necessary condition for point x star to be local minima. To be local minima is, there are 4 conditions, 4 necessary conditions for x star to be local minima. One of them is that if I form, assume that I form a Lagrangian here. I form Lagrangian in terms of my primal variable and some dual variable, alpha I. Then it's f of x minus sigma alpha I gix. That's my dual. So one condition is that derivative of L with respect to x at point x equal to x star should be 0. So if you take derivative of Lagrangian, it should be 0 at the optimal point. Because basically, that's the point. I mean, if it's 0, it means that the tangent of this and the tangent of f are parallel to each other. The tangent of the constraint and tangent of the function that you want to minimize. Means it's a point that the constraint and the function can touch, but they don't cross. So this is one condition. Another condition is that gi x star should be greater than equal 0. gi for all x should be greater than equal 0. So definitely for x star should be greater than 0. So it's called primal feasibility. Also, we have a dual variable, alpha I. This should be greater than 0. Lagrange multiplier also always should be greater than equal 0. This is called dual feasibility. So, but I'm interested in this 4th condition, that alpha I gix should be equal to 0 for all I. It's called complementary slackness. So this is, the condition that I'm interested in. Complementary slackness. Okay, let me, in the optimization that we are doing, take derivative of Lagrangian with respect to primal variable, which is beta and beta null, set it to 0. We made sure that this is satisfied. We literally put it to 0 and computed the dual in terms of primal. And, this is a condition of our optimization, so we're sure that it is greater than 0. But if I look at this, complementary slackness, what does it tell me? It tells me that alpha I times the constraint, gi, and the constraint was that yi times beta transpose xi plus beta null minus 1. That was g, right? because this was supposed to be greater than 1. So this minus 1, it should be greater than 0. That's my g. This should be 0 for all I. Okay. So what this condition basically means, I know alpha I is my dual variable, and alpha I cannot be negative. It's always greater than 0, or it's equal to 0. So there are two possibilities. Either it's 0 or it's greater than 0. Now, I suppose that it's greater than 0. I'm talking about alpha I that is greater than 0. So if alpha I is greater than 0, then what's going to happen? So what can I conclude if alpha I is greater than 0? Sorry? Yeah, this is 0, right? So if alpha is greater than 0, I can conclude that yi times beta transpose xi plus beta null is equal to 1. So yi beta transpose xi plus beta null is the distance of point xi from the hyperplane. The minimum distance is 1. And it turned out that it's 1 now. So what does it mean basically? It means this point is a point which is on the margin, right? That was basically that was our problem. And I was interested in this line, which has maximum margin. So this is basically, a margin. This is a margin, and I wanted to maximize this margin. So it means that this particular point is on the margin because, the distance of this point from the hyperplane is 1. So you solved your dual problem in terms of alpha, and you find a vector of alpha. Basically for each data point, you have corresponding alpha, which is a scalar now. For each data point I have alpha I. If alpha is greater than 0, means corresponding point xi is on the margin. So we call this points that are on the margin support vectors. Okay, so this is one. It means that xi is on the margin. Which is called a support vector. Okay. Now consider the case that I have a point that's not on the margin. For any point yi beta transpose xi plus beta null is either 1 or greater than 1, right? So if yi beta transpose xi plus beta null is greater than 1, means if the point is not on the margin, the point is further from margin. So what can I conclude here? Alpha is 0. Okay. So for any point that's not on the margin, alpha is 0. Now, think about the optimization problem that we're solving, we're maximizing this. The solution that we're going to compute at the end is very sparse solution. Alpha is 0 for any point that's not on the margin, and is non-zero for only points that are on the margin. It means that all of these points that are not on the margin have no effect in my optimization, right? So it doesn't matter that I have the point here or I have here. It makes no difference. Is it good or bad? Sorry?
It's good.
Why it's good?
Considering the margin, right? You're not concerned about the other points.
Exactly. It's very good, actually, It makes your model very stable and, robust in terms of outliers. I mean, outliers is always a problem. Suppose that I do perceptron, my points are here. If I put a point here, all of a sudden, this point changes the direction of my decision boundary completely. If it's very far, it make everything bad, because it try to push this decision boundary toward that point strongly, and makes everything bad. But with this basically optimization problem, it isn't going to happen that way. I mean, I'm just this point, support vectors have effect on my optimization. Other points don't have any effect. It doesn't change the optimization. Okay? When we do a soft margin, we can see it more clearly, the type of objective function that support vector minimize. The type of objective function that support vector minimize is like this. It's like hinge loss, It means that up to some error, I'm not going to penalize you. Up to some error, I'm not going to penalize you. This is in contrast with like quadratic, for example, that start to penalize with a small deviation from the true value. Or with norm 1, this is norm 1, this is 2, and this is type of objective function that support vector minimize. So it doesn't penalize up to a certain threshold. After that, it starts to penalize. In terms of regression, if you think about it, you have some points, and you want to fit a line to these points, In least square, it's as if you have a spring between all of these points. And say this is, a piece of, it's a stick, and you have a spring here. And you leave this until, it gets settled. That's what least square does, it's quadratic function does. But here, it's as if you take a little bit of rope. For each of this point, you have a little bit of rope, and then you have a spring. Up to a certain error, there's no force, there's no punishment. If your error is more than that, if you're that close to this point, in the length of this rope, nothing will happen. I won't push you in any side. If it's more than that, then I start to push you. So it means that, support vector machine, the objective of support vector machine has some sort of tolerance. It has tolerance with respect to error, a little bit of tolerance. The moral is that tolerance is good. If you have tolerance towards mistakes a little bit, it's more robust than start penalizing right away with small mistake. If you tolerate small mistakes, that are going to be more robust. Okay, you're going to see this objective function more clearly when we do the case that's not linearly, it's not linearly separable. Okay, so far we learned how to compute a linear decision boundary. Another beauty of support vector machine is that it can be easily extended to the case that this decision boundary is not linear. There's a nonlinear decision boundary between two set of points. And with almost the same objective function, you can find that boundary. Okay, the idea, I mentioned, the insight of this idea when we did the linear discrete analysis and quadratic discrete analysis. And that was the intuition that you have, you suppose that you have this cloud of points. And you have another set of points, another class inside this class. So this is a cloud of points, and there's another cloud of points right at the middle here. And I want to basically make distinction between these two set of points. To do classification, there's no linear boundary. So that would be my decision boundary. Okay? But if I magically give this data the third dimension, if I map them in a three-dimensional space, such that this middle points at the middle class are here and the other class is here, then there is a plane which can make distinction between these two. So there is a linear discrimination function between these two classes. So in higher dimensional space, we have like this scarce of dimensionality that in higher dimension learning is hard. But we also have less of dimensionality than in a higher dimension. Nonlinearity start to look like linearity, So, and basically, instead of you have an algorithm which is linear. Instead of changing your algorithm to nonlinear case, change your data. Make it linear first, and then apply your linear algorithm to that, okay? So, and we have seen this in linear discrete analysis and quadratic discrete analysis, that one trick to make linear discrete analysis quadratic was to change the data to map it to higher dimensional space explicitly. Now, kernel trick is basically a very elegant idea that does this implicitly, not explicitly. Because there exist some functions, which is called kernel functions, that, in the past, we have seen that you have x, and you map this x to higher dimension using like phi of x, right? And things start to become linear in this new space. Now, there are some sort of functions, which is called kernel functions. And kernel functions have this property that kernel of x and y is phi transpose of x times phi of y. So there are some functions that if you apply that function to, say, two data points or two vectors, it's as if you first map those points to some higher dimensional space and then compute a dot product between points in the new space. Okay, this is a Hilbert space, in fact. If you map these points in this Hilbert space, the dot product of points or the inner product of points in this Hilbert space correspond to some functions in the original space, and this function is called kernel functions. Now, the trick is you have a linear model. It's classifier, it's regression model, whatever it is. It's linear, okay? Rewrite your model in a way that it does not depend on coordinate of the points, but it does depend on the inner product of points. So never x appear in this formula by itself. Always you have x transpose x. So I have a model such that in this model I never have x by itself. Always I have x transpose x. Okay. Now, if I have function phi and map my point to higher dimensional space using phi, then instead of x, I have phi of x. Okay? But interestingly, there are some functions that I can apply to x itself, and the value of this function is the same as value of this in the higher dimensional space. So it gives me a tool to map the points in higher dimensional space implicitly, not explicitly. So I never know this phi. I never map the point in higher dimensional space. But since I know the inner product is equal to this function, I rewrite my original model in a way that it depends on inner product. And whenever I have inner product, I put the value of this function in a stat, as if I mapped everything to higher dimensional space. Okay, it happens automatically. Okay, let me show you like a couple of, the example that I gave you about these two set of points that you want to give them third dimension. If you want to make it more concrete, suppose this is the two classes that I have, and it's in two-dimensional space. Each point can be expressed by x1 and x2. Now I define a mapping phi, and this mapping phi works this way. I take the first coordinate squared, second coordinate squared, and the third coordinate would be square root of 2 times x1 times x2. So basically using this phi, I map anything from two-dimensional space to three-dimensional space. So any two-dimensional point would be a three-dimensional point on this form. x1 is squared, x2 is squared, and then a square root of 2x1 times x2. So if you do this mapping linearly, it's a good exercise, do it linearly. You can see that in three-dimensional space, the points have this form. The third dimension becomes, distinctive, and it's clear why. Because, the points in this circle have a smaller x1 and a smaller x2 compared to other points. And when you multiply x1 by x2, it makes distinction between points that are further apart compared to the points that are closer to the origin. So this third dimension becomes distinctive, Points on this side, on the third dimension, have a smaller value, and points on this side, on the third dimension, have a larger value. So in the third dimension, there's a linear hyperplane, this boundary, decision boundary, which can make distinction between these two set of classes. Okay? So as I said, we can do this implicitly. In this particular case, this phi that we introduced was x1 squared, x2 squared, and a square root of 2x1, x2. Okay? Now compute the inner product between these two vectors. Suppose that you have these two vectors, and compute the inner product between these two. This is your phi x transpose times phi x. Compute the inner product between these two. You can verify that the inner product between these two vectors is the same as inner product between these two. It's squared. Okay? if I compute like I have x1, x2 times x1, x2 squared. Okay, this is this line. This is prime, actually. So that's going to be x1, x prime 1 plus x2, x2 prime squared, which is squared means that this, squared, it's a scale. Okay? And now compute this one. It's going to be the same. It's x1 squared, x2 squared, x1, x2, x1 prime squared, x2 prime squared, x1 prime, x2 prime. Then it's going to be x1 squared, x1 prime squared plus x2 squared, x2 prime squared plus 2 x1, x2, x1 prime, x2 prime. And if you make this squared, it's going to be x1 squared, x prime 1 squared plus x2 squared plus times x prime, x2 prime squared plus 2 times this times this. So these two are identical, right? But this is my phi of this vector. I had a point in two-dimensional space. It's a vector here. I show it this way. And it's a vector here. So it's a phi of this vector transpose times phi of the other point. But this inner product squared is a function in the original space. I don't map them to higher dimensional space. I don't use any phi. There is a function, this function is squared. An inner product of the two vector and a square. There is this function in the original space that when I apply this function in the original space, it's as if I mapped them through phi to higher dimensional space, and then I computed the inner product. Okay? This type of functions is called kernel functions. And there are many kernel functions, 3 common kernels are linear kernel, which is basically you have matrix X and you have matrix Y, it's X transpose Y. That would be linear kernel. And there's polynomial kernel, and it's Gaussian kernel or RBF kernel. It's the most, very famous among all of these 3. And there are many more type of kernels, that you can apply to points. One way of looking at kernel is that kernel is a measure of similarity between points. Phi transpose times phi, inner product of these two phi, is a measure of similarity between phi x and phi y, right? Because these are two vectors. Inner product shows, how aligned these two vectors are, how similar they are. Look at this, xi minus xj squared divided by something. If xi and xj are the same, it's going to be 0, right? And e to the power of this 0 is going to be 1. But if they are far apart, if xi and xj are far apart, it's a large value, e to the power of negative large value would be close to 0. So if these 2 points are similar, it's close to 1. If they're dissimilar, it's close to 0. So we can think of kernel as a measure of similarity, As if you map your data point in a new space, you define a new measure of similarity between them. In the original space, they are not separable. I go to another space and I define similarity in a new way. In this new way, I change the geometry of this point. In this new geometry, the concept of similarity is changed. They are separable, okay? And there are all type of kernels, not only for simple vectors. In the literature, you will see, you are working with graphs, for example, and trees. There are kernels for graphs and trees. How similar two graphs are, how similar two trees are, how similar two subgraphs are. Okay, they may not have this closed form formula. You may need to run a code to find the similarity between these two graphs, but it's a kernel. Probably it's a kernel. And you are working with proteins, with molecules. There are kernels which shows you how similar they are or how different they are. Okay. So always, in the area of kernel, we have this observed and we have feature space. Observed space is the original space that we are working on, and feature space is the space of this phi. The beauty of kernel methods is that we never need to know this phi explicitly. So when you have this Gaussian function as a kernel, we don't know the phi corresponding to this. And we don't need to know. Okay? We don't need to know. So how can we use this concept in support vector machine and make take care of nonlinearity? Okay. That's my objective function. Okay. Look at this objective function. Unknown is alpha, and yi is my labels, and xi is my data points, right? You see, the objective function does not depend on the coordinate of the points, but it depends on the inner product of points. I never have xi by itself. I have xi transpose xj, the inner product of these 2 points, right? Now, suppose that I have a function phi which takes points and map them to higher dimensional space, and hopefully points that are not linear in the original space becomes linear in that space. So if I use that function, then here, actually my objective function here would be phi of xi transpose times phi of xj. Okay? But I know that, phi xi transpose phi j correspond to some kernel in original space. So I can take this and put a kernel between xi and xj. So nonlinear support vector machine, but don't forget that still we are doing hard margin. Okay, we are doing hard margin. But nonlinear case would be max of alpha I minus 1/2 ij alpha I alpha j yi yj. Now instead of xi transpose xj, I have k xi xj. And this k could be any kernel. In practice, when you want to compute this k, This could be e to the power of minus xi minus xj squared divided by something. You literally compute this and put it here, this value. And subject to the same constraint. Okay, now I solve for this and compute alpha. And I haven't paid any additional costs here. But now my boundary is nonlinear. Okay, thank you. Now my boundary is nonlinear, it's not linear. Okay? So I can compute alpha and it's going to be nonlinear. But just there is one point here. You know, when in the linear case, when we solve this and compute alpha, then beta was sigma alpha I yi xi, right? But in this case, it should be alpha I yi phi xi. But I told you that we don't know phi. You know, we never knew what phi is explicitly. What can I do here? Actually, it's very easy. I will tell you what to do here. Very easy. I mean, you can figure it out yourself. And you don't need to know phi. We will talk about it in the next lecture. Also, we'll see soft margin, the case that the data points are not linearly separable. But a part of basically, course, you have 4 assignments, and I told you at the beginning that you're going to have like a mini project. Mason kindly made the mini project on Kaggle class. It's a classification problem. He's going to explain about this problem. It's a classification problem. And from now until the end of the term, you can submit as many submissions as you want to Kaggle. It's a private competition only for our class. So you can submit as many times as you want using any technique that you like. We learned some classifiers so far. We learned some methods for dimensionality reduction. We're going to learn more methods for classification, bagging, boosting, meta models, and feature extraction. Use those, combination of those. Try to solve this optimization, try to solve this classification problem. You are not going to look at your code. It's just a submission. You submit this, and Kaggle will rank you. And based on this rank, that would be 10% of your, you have like 50%. You had assignments, 4 assignments, each 10%, and 10% would be this one. And do whatever you want to do, as many times you want to submit until the end of the term to get a better performance on this. But details, Mason is going to give you the detail.